Hey everyone, welcome back to my channel EduVibe. In today's lesson, we're moving to the next topic of the electromagnetic radiations. We're doing the photoelectric effect and the photocurrent. Now we connect the electromagnetic radiation to the electrical part. So we're doing the photoelectric and the photocurrent. So these are the two parts where are the more of the theory based thing, and we do some one formula in this too. But there's a more likely a theory thing we have to know in this. So you get the common questions from here. So what are those common questions we're discussing today's lesson? Okay, we're starting with the photoelectric effect. So when high frequency electromagnetic radiation is shown onto the metal cathode. So we have a cathode over there, and when any high frequency electromagnetic radiation can be shown on this cathode, the electrons, sometimes we call that as the photoelectrons, are emitted. Photoelectrons is the thing over there, which is kind of the electrons which are emit when we put the high frequency electromagnetic radiation shown on the metal cathode. Then they travel to the anode. You can see over there they travel to the anode. This is our anode, and register a photocurrent measured by a meter. We have a meter over there. This is basically the photocell. This whole thing doing the photocell type thing, where the cathode then show on the high electromagnetic radiation, and then they are emitted the photoelectrons. Electrons are emitted from here. So kind of the electron thing we have to discuss in this. The process is known as the photoelectric effect. So this whole diagram called the photoelectric effect, initially discovered by the Hertz in 1887. So Hertz is likely to know you this is a unit for the frequency. So we can add this topic to a frequency too. The photoelectric was first the real test of modern physics to try and hammer out the details of whether light is a particle or a wave. Now, on the rest of the unit we're left with, we consider that light is a particle or a wave. We have to find this is a particle or a wave. We can do the many of the different effects in this in the upcoming lessons too. That to find out that the light is a particle or a wave. One thing that the minimum frequency required to known as the threshold frequency. So threshold frequency is another term which denotes the F0, or you can say F. So this is all the minimum frequency we take when we do the anything in the photoelectric effect called the threshold frequency. Incident radiation below this threshold frequency will not cause the emission of an electron. So below this threshold frequency, the emission of the electron cannot be happened. So we can't say that this is a photoelectric effect if this is below the threshold frequency. So all depends on the threshold frequency, which is a minimum frequency required. So this thing you have to know about the photoelectric effect for now, and we discussing one thing more, which is the Einstein's contribution to this photoelectric effect. So this is the main of the contribution of Einstein, and we know that some cases we have. So these cases we have to discuss that how the frequency and threshold frequency can be compared with each other. So Einstein bounded over one only electromagnetic radiation of the sufficient frequency with the liberated electron. He realized that this was evidence that the light was not a wave. From their evidence, Einstein states that light is not a wave. So this is like a first argument, you can say, some prediction of the Einstein that the light is not a wave. Light does not behave like a wave. If light was a wave, instant electromagnetic radiation with the frequency below the threshold frequency should be able to accommodate in an electron until it has the sufficient energy to be liberated from a metal. So to be the light was a wave, to be light to be a wave, so incident electromagnetic radiation with the frequency should be below the threshold frequency, which should have the sufficient energy to liberate from the metal. That the electrons and liberate from metal have the sufficient energy to liberate from any metal. So that minimum threshold frequency should be required. So that's when this happens, we can say that the light was a wave in that case. So this is the same thing, we don't have to know this about now. Okay. At the end, Einstein has applied the Planck's theory of quantization to explain why the particles of the photoelectric effect. So to determine the photoelectric effect for more efficiently, at the last, Einstein applied the Planck's theory of the quantization. Conclusion of this, and this could be drawn from the Einstein's work. So what are those? If the instant frequency is below the threshold frequency, So no electrons can emit from this. So no matter how bright the light is, so if they're below threshold frequency, incident frequency, so electrons are not emitted. Even if it is above the threshold frequency, electrons are emitted instantaneously, no matter how dim the light. These two conclusions, the Einstein's words can be done with that. Einstein also posted that if was a minimum frequency required to liberate an electron, there is a minimum energy required to do so. So this is a photocurrent, and we have frequency. So a threshold frequency can like goes with graph like this. If we compare with the photocurrent, we do talking about the photocurrent in the next few slides. So minimum energy required to liberate an electron from a metal surface is known as the work function. So some work they're doing, when they're doing the minimum energy required to liberate an electron on a metal surface is known as a work function denoted by the W. So after that, we have some cases related to this that if frequency is less than threshold frequency, the photo energy is smaller than the work function. You have just know about this only, and we have a no current is measured on that. So that's the case. If they're equal to each other, the photon has just enough energy to remove the electron from the metal. So have they enough energy to remove electron from a metal? They have enough energy, not lots of energy. So then the photon energy is equal to the work function in that case. If frequency greater than threshold frequency, the photon is greater than the work function, the photon is fully absorbed by the surface electron in the metal. That's all which I highlighted. That only thing you have to know about this, that if that cases are applied to any of the photon energy, you can denote this by like this, that this is that and that's this. So the photon energy is always be depend on that things, and we use the Planck's constant to in this to more elaborate the answers. Then calculating the work function. You are probably like asked about the questions like to the work function. So we have to know the formula, and this formula is on your formula sheet. That work function is equal to the Planck's constant times threshold frequency. Work W is the work function, joules or EV. This is a Planck's constant. We have two values, and this is a threshold frequency as hertz. When E photon is greater than W, we can examine the relation between the energy of the instant electromagnetic radiation, which is the photon minus gamma work function, and the maximum kinetic energy of the liberate electron. So if your E photon is greater than W, which is the main thing in this, we have to examine some relationship between them. What is those relationship? So we have a diagram over there. We can see that our incident photon is an incident photon going over there, and then they do some kinetic energy, they move into the different path. For this you have to know some formula, that et before liberation is equal to tt after liberation. But this thing is from there, but the formula you actually know from this, the E photon is also equal to W plus kinetic energy, which is max. The maximum kinetic energy you have to know, and this formula, this is not on your formula sheet. You have to memorize this, and this is the main thing. If you want to use this formula, you can use this formula more oftenly, but this formula is like a very important to know about this, that this is very important. And one thing more, that we have a threshold frequency. That threshold frequency is also equal to the C upon max wavelength. So if you have a wavelength, you have a C is always same value. So you can find out the threshold frequency from there too. So that's the thing you have to do in the questions when we're doing. So this formula is very important, this one. So you have to know this now. Let's move on to the example. So the minimum energy to emit the electrons from a polished transparent metal surface is 4.07 eV. Determine the maximum wavelength of the electromagnetic radiation that can emit electrons from this surface, and classify the electromagnetic radiation. So now we also doing like photon theory electromagnetic spectrum. From there you have to find from them, because we're talking about the electrons, wavelength, and all things. So we have to go from that table and have to know what is that electromagnetic radiation is there. So first we have to find the wavelength, and then we can say about that things. Okay, so we have to find the wavelength, but we have like W over there. We have W. So wavelength I measured by the things like we do this formula, C upon wavelength max. From here you can find. So You know that W is equal to H upon threshold frequency. H, then threshold frequency is C upon wavelength, maths, W. So you have to find the wavelength maths is equal to HC upon W. So wavelength maths is equal to, you can, so your W is in EV, so your H value you can take from EV dot second. That will cut this. C you have always the same. And yeah, this is a 4.0 EV. So when you calculate this, you get 3.05 into 10 raised to minus 7 meters. If you see your electromagnetic spectrum, you can see that at 10 raised to minus 7, you have more likely the UV radiations or the ultraviolet. So you can see this more likely this from your electromagnetic spectrum. So that's how you can deal with those questions. You can't write this that's much small question. There's a simple question. We'll do some more practice in this. We're doing some of the practice question of this. So you have to come to know about something like a core thing in this now. And oh, we have the example in this. So this is like a very much like complex example we have to deal. So let's deal with those. So determine the maximum energy, maximum speed of the electrons emitted from surface of an unknown metal if his work and work function is 2.12 eV and is illuminated with the monochromatic light with the wavelength of 450 nanometers. Now you have given the wavelength. So you have to find the speed. From where you get the speed? You get the speed from kinetic energy, because you know that kinetic energy. We can about the kinetic energy in this theory, so we deal with the maths. We have half mv square. From here, your velocity should also be the mass. So from here, you can find the velocity, which is velocity mass is equal to 2 ek mass divided by m, which is the mass of the electron and the whole root. So from here, you don't have the ek mass. So ek mass can be found from something else. Okay, we have to find this thing. So let's do over there. So you do some one formula that photon energy is equal to W plus EK mass. From here you can find the EK mass now. So EK mass is equal to the photon energy minus W. So EK mass is equal to photon energy is equal to the Planck's constant or Planck's equation minus W. You have W, you have wavelength, you have H and C, so you can find now. So let's find over there. So EK mass is equal to H. So H we get again 4.14 because we have EV of the W. This 3.0 10 raised to power 8 meter per second. And this should be minus by 2.12 EV. This whole thing is multiplied by the wavelength. 450 nano has a value of 10 raised to power minus 9 meters. You can solve this, divide this, and then minus with 2.12 EV. You will get about 0.64 EV. But your candidate should be in joules to be put in that thing. So convert this into joules by multiplying this by 1.60 into 10 raised to power minus 19 joules divided by 1 E. So you will get EK mass of about 1.024 into 10 raised to power minus 19 joules. So that's your EK mass, and EK mass must be in joules to find the V. So put this over there. We have a 1.024 into 10 raised to power minus 19 joules, and divide this by the mass of the electron, which is 9.11 to 10 raised to minus 31 kgs. Hold the root of this. When you calculate this, you get about 4.7 into 10 raised to power 5 meter per second. So this is your velocity mass, or the speed of the maximum speed of the electrons. So that's how you can find, and this like a more complex one. We can use the Planck's equation, we use the EK mass formula, like E photon formula, and we use the energy formula to find the speed of the electron. So that's all the what you have to do to get the full marks in that questions. As a part question, you get the one of the questions very much like in the diploma or the examinations. Let's move on to the photocurrent now. As previously mentioned, while the intensity, which is the number of photons of the light, does not change the kinetic energy of an individual electron being emitted from the photoelectric surface. So it's mentioned that if the intensity of the light does not change, the kinetic energy of an individual electron is being not emitted from a electroelectric surface. So it does change the total number of electrons emitted. So there might be changes in the number of electrons that we emitted and thus have an effect on the current that which we registered on the emitter. So they affect the effect on the current something which is registered on the meter. So the current thing you have to know in this, like if you have a higher intensity and if you have a lower intensity. In the bright lights, you always have the higher intensity. In the dim light, you will get the low intensity sometimes. So you can see that formula that your current, which is I, is equal to a charge upon T, which is also equal to NE upon T, which is Q is equal to NE upon T. That we do in the forces and fields. So this is into N upon E. So we have something about the relationship can be inferred from here that if the intensity of the EMR is increased, EMR means the electromagnetic radiation, the photocurrent will also increase, which means we have a more electrons per minute. So all the photocurrent is depend on the electrons. We compare this electrons with the how much intensity, how much the current we have. So if we have a higher intensity of EMR, so we get the photocurrent of will also be increased. If it is a decrease, the photocurrent will be decreased and we have fewer electrons per time. If the frequency of EMR, if this frequency of EMR is below the threshold frequency, which we done in the photoelectric 22, the no photocurrent will be registered as the no electrons were emitted from a photoelectric surface. So if the below the threshold frequency always, so there's a no photoelectric surface can be emitted any electron or the photocurrent will not be registered anything and no photocurrent will be happen. So that's all things are integrated with each other. Like photograded surface, the current will effect will connect to the photocurrent. And in this more thing that the more intense light will liberate from more electrons, which will register greater photocurrent, less intense light will liberate the fewer electrons, which will register smaller photocurrent. This is all the conclusion we do in that points. So that's all the same thing. This is in the short form. And one thing more, this is very important. These 2 points are very, very important. You have to know these 2 points that speed of the emitted electron, if we any emit electron, the speed of any emitted electron is equal to the frequency wavelength of the photon. Is like the go side by side. Like if this is happening, so this will also happen. If this will happen, so emitted electron can be happen. And the intensity of the incident radiation is the kind of the photocurrent and the number of electrons emitted. So that diagram you have over there. So that's the 2 points you have to know in this. So that's the end of this topic of the photoelectric effect and the photocurrent. So that's the very important topics, and we have we do the more theory part in both the things. We have only one calculation question in this, and that formula you have to know. So that's all for this lesson. Now in the next lesson we do the graphical analysis in the photoelectric effect because you get the questions related to graphical methods. So we do 2 graphs in the photoelectric effect. So in the next video we do that, and for this is all for this lesson. Learning was simple, EduVibe, learn smart but not harder. Please like, share and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till I say get it with EduVibe.